Very good morning to everybody. Welcome to the seventh session of classical mechanics. In the last session, we have discussed applications of Lagrangian equation for a simple pendulum. In this session, we shall apply Lagrangian equation for a linear harmonic oscillator. So Lagrangian equation of motion for simple pendulum is found to be theta double dot plus g by L sine theta is equal to 0. For small amplitude, the equation of motion reduces to theta double dot plus g by L is equal to 0. The learning objectives of this session is to understand how to derive kinetic and potential energies for a constrained motion and the application of Lagrangian equation for linear harmonic oscillator. After the completion of this session, you will be able to solve Lagrangian equation for linear harmonic oscillator. Linear harmonic oscillator. Let us consider a body of mass m attached to a string with a spring constant k. It is under equilibrium condition. If a force is exerted along the direction and allowed due to restoring force of the spring, the position changes. We know that then the body of mass m will set into oscillation. Then the kinetic energy of the system is given by half m x dot square. We know that the force is given by F is equal to minus kx. For a conservative forces, potential is derivable by the integration of the force. On integration of F is equal to minus kx, we get the potential energy using F is equal to minus del V operation. So we have obtained kinetic energy of linear harmonic oscillator to be half m x dot square and the potential energy is equal to half kx square. We know that the Lagrangian term is given by L is equal to T minus V. On substituting kinetic energy and potential energy, Lagrangian term for harmonic oscillator is half mx dot square minus half kx dot square. We observe that x and x dot. So the Lagrangian is a function of x, x dot and t. So the Lagrangian equation is d by dt of dou L by dou x dot minus dou L by dou x is equal to 0. Differentiating L term with respect to x dot, we obtain mx dot, and differentiating dou L by dou x, we get minus kx. On differentiating with respect to t for dou L by dou x term, it reduces to mx double dot. On substituting dou L by dou x, we obtain minus of minus plus kx, that is equal to 0. On simplification, x double dot plus k by m, x is equal to 0, where k by m is nothing but omega square. So the solution, this is the required equation for a linear harmonic oscillator, and the solution for this second order differential equation is given by x is equal to a cos omega t. So in this session, we are able to derive kinetic and potential energy for constrained linear harmonic oscillator. And we also obtained the Lagrangian equation of motion for linear harmonic oscillator. So, to understand how far we have understood this session, let's have a small MCQs. Question number 1. The coordinates chosen for generalized coordinate in harmonic oscillator is option A R, B L, C X, D none of the above. So we have seen the coordinate chosen is X. Question 2. The potential energy in a linear harmonic oscillator is option A kx, B of kx square, C 1 by 4 x square, D none of the above. So in the above equation, we have obtained the potential energy of a linear harmonic oscillator to be of kx square. So the option is B. Question 3. The equation of motion for harmonic oscillator is option A x double dot plus omega square x is equal to 0, x double dot plus omega x is equal to 0, C x double dot plus x is equal to 0, D none of the above. So we have obtained the equation of linear harmonic oscillator found to be x double dot plus omega square x is equal to 0. And the option is A. So the sources: Classical Mechanics by Goldstein, Classical Mechanics by Gupta, Kumar and Sharma, Classical Mechanics by Takwale and Puranik, Classical Mechanics by J.C. Upadhyay. Thank you all. Hope you enjoyed this session.